away and get our notes out. And let's take a look at where we left off last time. We had graphed last time the tangent and the cotangent, right? So today we're going to get the basic secant and cosecant shapes. But I actually listened to or attended a webinar yesterday, a pre-calculus webinar. Don't you wish you were me and got to do those fun things? But there's a few like little shifts that colleges are expecting now, according to this webinar anyway. So I'm going to make a few modifications in this unit. We're not going to do every graph on these notes. We're just going to do what are currently viewed as the important ones. So certainly secant and cosecant are important. You need to know what they look like. We're not going to be moving them around, stretching and shrinking them, but you need to know what the basic shape is. So tell me what you know about secant, just in general. When I say secant, what pops into your head? Reciprocal of cosine. So here's what I want you to do. This is my suggestion. You can do whatever you want, but my suggestion is sketch either with a dashed line or a different color or really lightly. Sketch your cosine curve, your standard old cosine curve. So you know it starts up here. I'm going to use a dashed line. Now we should already know that. Some of you had that on your quiz. That is a cosine curve. Now, you're going to take the reciprocal of it. What that means graphically is, right here at pi over 2, the cosine is 0. It's a 0 right there on the x-axis. If I take the reciprocal of 0, I get 1 over 0, which is undefined. So there's an asymptote right there because the reciprocal is undefined. Where else is there an asymptote? At 3 pi over 2. Any place it crosses the x-axis, that value is 0. So when you do the reciprocal, it's going to become undefined. Okay? Now, when I say take the reciprocal of a fraction, what do? Flip it. Flip this graph. So see this piece right here? Just take him and turn him upside down. So he's going to look like this. I literally take this thing and flip it upside down, this piece right here. Now, this is where it looks weird again, but see, this is half of a hill. So when I flip it, I'm going to get half of a valley. And then over here, I'm going to get the other half of the valley. That pink thing is the secant. So how do I draw a secant? I draw a cosine, drop in asymptotes where it crosses the x-axis, and then just turn the hills into valleys and vice versa, flip them over. Now, the period of this is exactly the same as the period of the cosine. Would you agree with that? Mm-hmm. But what about amplitude? There is none. That's right, there is no amplitude. We talked about this a little bit last time. When you graphed a tangent and a cotangent, we said there was no amplitude. Why? Because the curves go up and down forever. There's no height. Same thing here. There's no height at all. Now, is the one, excuse me, still kind of important? Yeah, because the one tells me where the bottom of my valleys are, but that isn't the amplitude. There is no amplitude. All right, cosecant. How do you think I'm going to do a cosecant? Start with a sine. So I'm going to draw my regular old sine curve. And you can do it in a different color, or you can do it with a dash line, whatever works for you. Now, is this guy going to have asymptotes, do you think? Yep, where are they gonna be? Wherever we cross the x-axis. So you're gonna have one right here, and right here. Then you're gonna take this hill and flip it up. And this valley, and flip it down. Your secant and cosecant are just a bunch of parabolas alternating up and down. That's all. How about amplitude for this guy? There isn't one, and the period is still too high. Braden?
Do we have to leave the dotted lines? Like,
You do not. They don't have to be there at all. I use them, but the purple is the answer.
okay.
If you have the dotted line there, that's absolutely fine. But if you, there's absolutely no requirement that you draw that. All right, everybody good so far?
Yep.
Now we're gonna mess around with a couple of these. We're gonna mess around with the tangent a little bit, because tangent's important. Tangent's one of the big functions. It's important. So just as a refresher, I'm gonna remind myself that a tangent looks like this. Right?
Yeah.
Now what have I done to my tangent? Well, let's talk about what does this 2 do? This 2 right here. It alters the amplitude. Now wait a second. This is a tangent. There's no amplitude. So realistically, that 2 is gonna make your tangent curve straighter. It's gonna, instead of like this would be a curvy one, it's gonna make it straighter. For us, since we're just doing rough sketches, we're kind of gonna ignore that 2. The only time it's gonna matter is if it's negative, because if it's negative, it's physically gonna turn the picture upside down, right? But in terms of our sketches, that 2 isn't gonna, we're not gonna worry about it. This 2 matters though. What does that 2 do? Divides the period. Now, the period of a normal tangent, asymptote to asymptote, is pi. So the normal period is pi. But this one has been divided by 2. So that means that asymptote to asymptote, here's my tangent picture. Asymptote to asymptote's only half a pi. So where do these labels have to be? A 4th. Yep, so negative pi over 4 and positive pi over 4. Won't that give you the whole distance? I mean, a pi over 2?
Yeah.
And there it is. Easy as can be. All right, we're gonna skip down to G. Now we're gonna do G. Please don't worry about not doing those, kids. It's not gonna matter in your life. I don't think negative 3 cosecant 1/2 x minus pi over 3 is probably gonna have much impact on your life.
Do you think negative 4 is COT?
I think this one probably will have some impact on your life.
Okay.
At least it might have impact on your next test, okay? So we'll get it done. All right, so let's talk about this one. Again, you guys do whatever you want. I always find it helpful just to keep the normal graph, the regular old graph in my head. And since not much can stay in my head anymore, I have to draw it. So here it is. This is the cotangent, regular. Now, what have I done to it here? Done a couple of things to it. What have I done? Well, that 4 is gonna affect the curvature, and that's all. So I'm not gonna worry about the 4, but the negative means that it's actually now gonna look like a tangent.
Yeah.
Now I need some labels. What is my period? My period's supposed to be pi, but what have I done?
Divided by 1/4.
Divided by 1/4, which is 4 pi. Asymptote to asymptote is 4 pi. Since that's 0, since this asymptote's 0, this was just 4 pi, right? And the middle's 2 pi, and your picture's done. All right, J. If we're doing them, you're responsible for them. If we're not doing them, you're not responsible for them, so please don't worry. All right, this is a tangent. Now this tangent's a little bit different though because of this, right? What does that do? Shift you side, well, yes, I'm gonna factor this half out, but the fact that I have something here means I'm shifted. So the normal tangent, remember, looks like this. This is the normal. This one is not going to go through the origin though, it's been shifted. So I gotta figure out how much it's been shifted, and I figure that out by factoring out the half. The half must come out. Now, kids, if I told you to factor this, right, if I said factor that, every single person in this room would almost brainlessly do this, right? And that's how it factors. That 3 came because factoring is division. So when you factor out a 2, you're dividing by 2. So if I'm factoring out a half, I'm dividing by a half, which is timesing by 2. So this is going to be pi over 3. If that's too much, what were you talking about, Miss Ford? I don't get it. Figure out what this number is so that when you multiply these together, you get that. That's the key.
You only have to factor out if there's like another number.
Yes, yes, yes. Because the reason we're factoring, Meg, is to figure out what my phase shift is. This is not the phase shift. You have to get that half out of there to see it. Now I can see my phase shift. My phase shift is pi over 3. Now what does that mean? That means, this is my tangent picture. Let me get the cotangent out of there so I'm not confused. This is my tangent picture. That means that whatever happened at the origin moves. New origin. The new origin is here. Which means there's an asymptote back here somewhere and an asymptote out here somewhere, and the curve is doing this. That's what that means. So when we phase shift a tangent curve, we phase shift the origin, the point. Okay? Now, what's the period of this function? It's supposed to be pi, but it's now 2 pi?
Yeah.
So what does that mean? That means that asymptote to asymptote is 2 pi. Asymptote to asymptote is 2 pi. That's the middle. My picture doesn't look too good, but that's the middle, right? So can we figure out what those asymptotes are if we know that the whole thing is 2 pi? Don't we just start here and add pi? So this would be 4/3. And then we subtract pi. So this would be negative 2/3. And you're done. Now, in terms of filling in period, we already did that. Phase shift, vertical shift, amplitude, and frequency. frequency. I got those in the wrong order. I got them in a different order on there. But our phase shift was pi over 3. We figured that out. We do not have a vertical shift. That would be a number on the end, right? We do not have an amplitude because it's a tangent, and tangents don't have amplitude. And our frequency is the reciprocal of the period, which is 1 over 2 pi. Okay? We're gonna do one more. We're gonna do K, but we're gonna change the cosecant to a sine. So cross out cosecant, and we're going to graph it as though it's a sine. This is as bad as it can get, okay? It's got everything going on, and it's full of fractions. So if you can handle this one, you can handle anything. All right, so here we go. Let's start the same way we did last time. Let's get that guy out of there. Remember that factoring out of 1/3 is dividing by 1/3, which is like timesing by 3. If that's too confusing, if I take this times this, do I get that?
Yeah.
Yeah, good. That's all I need to know. Okay. Well, this is definitely a mess. All right. It's a sine curve. And I saw some of you doing this in your homework. We do this sometimes. I don't know. It seems to work for some of you. The vertical shift is 1 plus 1. So if you have trouble translating your points, I mean, like moving them up and down, you can actually build a new axis here if you want. So this is the normal axis, but everything is going to get shifted up 1 unit. Would you agree? Now, the amplitude of the curve, this is 1 now. The amplitude of the curve is 2/5. So be careful. You're going to go up and down 2/5. But these labels aren't going to be 2/5, are they? This is going to be 7/5, and this is going to be 3/5. Because 1 plus 2/5, 1 minus 2/5. Are you with me? Now those are going to be my high points and low points. My curve has shifted 3 pi over 5. So this is now 3 pi over 5 right here. So that's where my sine curve is starting. It's a positive curve, so I'm going to go ahead and put my hill and my valley. There we go. Are you still with me? Now, I need this label, this label, this label, and this label. That's the high point, my 0 where I cross, my low point, and my end point. What is the period of this curve?
6 pi.
Supposed to be 2 pi, but it's been divided by 1/3. So that means that the entire thing, start to finish, is 6 pi. Can I think of 6 pi as 30 over 5?
Yes.
So if I start at 3 over 5, and I travel 30 over 5, where am I going to be? 33 over 5? And then this is going to be right in the middle of the average of 3 and 33. Well, 3 and 33 makes 36, and half of 36 is 18. So this is 18/5 right here. It's the midpoint, or the average of your beginning and end. Now, this one's not gonna work out so nicely, because when I average 3 and 18, I get 21/5, and 21/5 can't take half of 21, so I'm gonna have to make it 21/10. I add them, so I got 21/5, and then take half of it, divided by 2, take half of it. Same thing here. 18 and 33 makes 51, and half of 51/5 is 51/10. Alright, who's got, let's fill in all the stuff. We need, we already did period. Here was our period. So our frequency is 1/6 pi. Amplitude is, now be careful on this, your amplitude, even though you didn't label it 2/5 and -2/5, that number's still your amplitude. Isn't that how high these waves are? So the amplitude's 2/5. Phase shift was 3 pi over 5, and vertical shift was 1. Seriously, that's as bad as it can possibly get. You alright with that? Alright, we're gonna do one of these problems and then we'll be done for the day. This is no calculator. Tomorrow we're gonna do some with our calculator, but right now it's no calculator. We're solving a trigonometric equation. We're doing it in radians. That's what 0 to 2 pi means. Those are radian measures. And we want to know all of the angles that have a secant of 2. I want you to think about that for a second. What would that, here's the angle right here. What would that angle look like? I mean, what would that triangle look like if the secant is 2? Hypotenuse is 2, and adjacent is 1. So this side is √3. You can use the Pythagorean theorem, but hopefully by now you don't need to. You see a 1 and a 2, that's going to be a √3, which means this angle is how big? 60, which is great, except I'm in radians. Pi over 3. I like how she's thinking. What's the relationship between 60 and 180? Isn't 60 a third of 180? So 60 is going to be a third of pi. Now, just when you thought it was over, it's not. Because there is another triangle that would have the adjacent 1 and the hypotenuse 2. In other words, there's another place where the secant is 2. Any thoughts about where that would be? Is it over here, here, here? Where is it? It's got to be quadrant 4. Because we need x to be positive, don't we? Won't that triangle also have a secant of 1, or excuse me, a secant of 2 over 1? Now, if that's pi over 3, this is pi over 3. The angles always match. You're never going to have different angles in the same problem. How do I write that one? What would that angle be? Well, what's all the way around? Or 2 pi, right? 2 pi's all the way around. So I didn't go all the way around. I went all the way around except pi over 3. So that's 5/3. That's 5 pi over 3.
Is it not 2 pi?
This is
Is it
2
not
pi over 1, so that's 6.
Wouldn't it be 4/3 pi because you're taking away? You're taking away 2 of those thirds.
No. This is our starting point.
Oh, yeah.
That's our starting point. This is zero. So that doesn't have anything to do with this. We're going all the way around to get to here. It's 300 degrees, which is 5 pi over 3. So there's 2 answers to the problem. Pi over 3 and 5 pi over 3. Those are your 2 answers. All right, good job. I'll see you tomorrow.